Alright, so for this video, we will talk about the in-class assignment for the chapter 18 to 19, which is about the multiple regression. In this assignment, I combined the simple regression and multiple regression questions together so that you can get a better idea about the differences between the simple regression and multiple regression. Alright, so let's look at the first question. It says the total credit card volume for Visa, MasterCards, American Express, and Discover has increased dramatically in recent years. 10 years of credit card volume in billions of dollars was recorded and modeled. And Model 1 and Model 2 are both models for the credit card volume. Alright, so A question. Using Model 1, explain the meaning of R squared in context. Alright, so actually for this question, we will focus on Model 1 and Model 2, right? So let's go up to see what's the difference between Model 1 and Model 2. Okay, so this is Model 1, right? Okay, so we still have 3 tables. The summary of fit table tell you the general information about this regression. A ANOVA table will tell you about the variance of y. Where does the variance of y come from, right? Come from the model, come from the error, you have the total variance. And then the next table will be the parameter estimates, which will give you the detailed sample equation, right? So this is Model 1. You will see that we have only one explanatory variable, which is the year, right? So actually, this is about beta 0. This is about beta 1. So year is our, since we only have one explanatory variable, so we don't need to say it is x1, so it's just an x, right? So what is the model? What is the population model for Model 1? Since we only have one explanatory variable, there will be mu y equals to beta 0 plus beta 1 x. So this is the population model, right? So then you have a sample so that you can ask a jump to create the sample linear regression equation, right? So here, this is for the population model, right? And then based on the sample, you will have the sample equation with the detailed value, with detailed estimation for the beta 0 and beta 1, right? So we will use that for estimating or prediction, right? So we'll have y hat equals to, now this is b0, this is b1, right? So we'll have the sample equation, which is negative 140664.7 plus 70.853x, right? So here x is the year, right? The y hat is actually the credit card volume. All right, so we kind of get a general idea about the Model 1, right? So Model 1 is simple linear regression because we only have one explanatory variable x, which is the year, right? And then we have the R squared, which is 0.946, so it is pretty good, right? And then adjusted R squared is 0.939. We can use this adjusted R squared to compare if we have a second model for the credit card volume, right? And then we have the root mean square error. We have totally 10 observations because we recorded 10 years, right? Okay, so this is our Model 1. All right, so let's look at Model 2. So model 2 still 3 tables, right? Summary of fit table, ANOVA table, and parameter estimate table, right? So to decide what is this model about, we first look at the parameter estimate table to decide how many explanatory variables in this regression, right? So here we have intercept for beta 0, and we have 2 rows, right? So the year is the first explanatory variable, and then we have another one. So what is this? Actually, it doesn't matter you use R or you use jump or sus, the system will create a kind of a strange output with this kind of name. So what is that? So it's actually X bar. So you don't need to worry about the name of it. So actually here it just tell you this is year minus X bar times year minus X bar. So this is actually for even not related with anything about our X bar. So it's kind of a strange name. So this one is just a X squared. So it's just a year times year, but nobody knows how this was created for the programming. So we just name it as the year times year, which is the X squared. Alright, so that means for this regression, is this still simple regression? No, it is multiple regression. Although they only focus on the year, but we have 2 explanatory variables. One is year itself, the other one is year squared. So actually you can consider year as x1 and x squared as x2. So what is the population model for this regression? The population model will be changed to mu y equals to beta 0 plus beta 1 x1 plus beta 2 x2, where this x2 equals to x1 squared. Or you can also state it as beta 0 plus beta 1 x plus beta 2 x squared. So it doesn't matter which way you use, as long as you can find the relationship or you can state what is the model of this regression will be fine, right? And then we have the 3 estimates for beta 0, beta 1, and beta 2. So what is this is called the population model, right? The population regression model. And then next, based on the sample, we will have the sample regression equation, right? So we plug in the estimates for beta 0, beta 1, and beta 2. So what is the sample equation? It will be y hat, because we want to use this equation to make the prediction. So we will not focus on the mu of y anymore. We need to use the y hat, which is equals to B0, which is negative 140716.9, plus beta 1x, which is 3.85x. Here I will prefer, for myself, I will prefer just to use x and then 6.327x squared, because it is easy to see the relationship. Otherwise, you need to state like this: y hat equals to negative 140716.9 plus 3.85 x1 plus 6.327 x2, and then you need to state, okay, x1 is the year and x2 is the year squared. Otherwise, nobody will know about what is x2, right? Because we only focus on the relationship between the year and credit card volume. All right, so now from this parameter estimate table, we kind of figure out what is this regression, right? What's the difference between the model 1 and model 2? So model 1 is the simple regression, model 2 is multiple regression. But actually, the simple regression is just a kind of special case for the multiple regression, right? So we still have the R square, we still have the adjusted R square, and we have the root mean square error, or the MSE, right? So here we have the MSE like this, right? So this is the MSE for the model 1, this is the MSE for model 2, right? The difference between the simple regression and multiple regression will be another thing is when we want to test about model 1 for the overall significance, what do we need to test? Still remember, for simple regression, the overall significance we need to test about just beta 1, right? Beta 1 equals 0, beta 1 not equals to 0, because we only have this coefficient, right? But for the multiple regression, what do you need to test first about the overall significance? We need to use F-test statistics, right? We need to use the F-test, not the T-test. For this one, we need to have the T-test statistics. But for multiple regression, we first need to test about the overall significance about this model. And only when this model is significant overall, then you can test for each variable. All right, so this is another difference between the simple regression and multiple regression. All right, so now we have kind of a good idea about the model 1 and model 2. So I kind of forgot what is the question about for the A question. It says using model 1. Okay, so just to focus on model 1, explain the meaning of R square. Okay, so let's go to model 1. R square. So R square is 0.946, right? Okay, so first I know that based on model 1, R square is 0.948, right? Kind of bad memory. 0.946. Okay. The kids are getting me crazy. All right, so I have R square is 0.946. Then you need to explain the meaning of R square, right? So generally we say R square shows the proportion of variation in observed is the proportion of observed variation in Y that is explained or accounted by the regression or the modeling of X, right? So here, when you make the detailed interpretation, you need to plug in the detailed meaning for X and Y variables, right? So what is the meaning of R squared in context? We say 0.946, that means 94.6% of the observed variation in the credit card volume, credit card in Y is explained, or you can use accounting, it doesn't matter, it's explained by the regression of X, right, which is the year, right? So again, we say it shows that the 94.6% of the observed variation in credit card volume is explained by the regression of the year. All right, so this is the first question. It's just to ask you to interpret the R square, right? So nothing difficult. Number B, using model 1, explain whether the model is significant. State the test you used and specific value on the output. Right, so as I said, we say model 1 is the simple regression, right? So for simple regression, how we can test about the significance of regression, we only need to test about beta 1, right? So we do not use the F-test. F-test is only for multiple regression, not for simple regression, right? So what we need to do, it says state the test. That means you need to state the hypothesis, right? So first, the null hypothesis, alternative hypothesis is about beta 1. Remember, we always test about the population parameter. So we cannot test the B1. We need to test about beta 1, right? So null hypothesis, beta 1 equals 0. Alternative hypothesis, beta 1 not equals to 0. All right, and then for this test, we can find the corresponding about B1 in the parameter estimate table. The B1, we have the corresponding t-test statistics and p-value, right? Okay, so we have 11.82. So we have the t-test statistics equals to 11.82, and then we have the corresponding p-value is very small, less than 0.001. So what does that mean? It means we need to reject the null hypothesis, which means we have enough evidence to support that the regression is significant or the regression is meaningful, right? Let's say significant or meaningful. All right, so the test is done, right? So you don't need to calculate anything. Everything is in the output. What you need to do is to state the right hypothesis, give the right p-value and the t-test statistics, and then make the right conclusion. That's all. All right, okay, so number C, what is the standard error of residuals? Okay, so what is the standard error of residuals? First, what is that? It is SE, right? Standard error of residuals is SE. How do you find the SE? It is also called the root mean square error, right? So this is just a SE, right? The standard error, the standard deviation of a residual, right? So which is 54.46. Right, so that's it. 54.46. That's it, right? So you don't need to calculate anything. You don't need to calculate the square root of MSE. You can do that, but it is not necessary, right? Okay. So A, B, C are all focused on model 1. So number D. Using model 2, explain whether there is evidence that the square term is significant and what that means about the relationship between the credit card volume and the variable year. All right, so what does that mean? It means we want to test whether the square term is significant. All right, okay, so actually what we are testing about, what is the square term in model 2? Which one? This is the square term, right? We want to test about whether this square term is significant or not. Then what is the hypothesis? What do we need to test about? We have beta 0 for the intercept. We have beta 1 for the year. Then we have beta 2 for the square term, right? So if we want to test whether the square term is significant, we are testing about beta 2. All right, okay, so then test about that. That means state the hypothesis, right? Beta 2 equals to 0, beta 2 not equals to 0. Right, so we just want to test about this term, whether this square term is significant or not. We do not want to test about the overall for now, right? So then to test about beta 2, what you need to do, you need to look at just focus on beta 2 and then find the t-test statistics and p-value for this term. Right, for this variable. All right, so that means you have the corresponding t-test statistics, which is 7.55. You have the corresponding p-value is also very small, 0.001, I think, right? So what is our conclusion? We say the same thing, right? So we reject the null hypothesis. We have enough evidence to support that the square term is significant, right? Okay, then next, number E, which model is better for modeling the credit card volume, Model 1 or Model 2? Give two pieces of supporting evidence, including the specific values for each. All right, so we want to compare the Model 1 and the Model 2. Let's come back to the output. All right, so if you want to compare these two models, what do you need to compare? Can you compare R-square? Remember, the Model 2 have a additional term, right? We add another variable into this regression. That means theoretically the R-square will always larger than, so the R-square should be always larger than the R-square in the simple regression, right? So we have 0.994 is larger than 0.946. But we cannot use R-square to compare the models. Why? We need to use adjusted R-square, right? So here, the first thing you can compare Model 1 and Model 2 will be adjusted R-square. So here we say give two pieces of supporting evidence, including the specific value for each. So this is my first supporting evidence. That means I have the specific value for each, right? So for Model 1, I have the adjusted R-square, which is 0.939. And for Model 2, I have the adjusted R-square, which is 0.992, right? I think so. Yeah, 0.939 and 0.992, right? Okay, so which model is better? We want the adjusted R-square to be as large as possible. The larger, the better, right? So that means Model 2 is preferred. All right, so this is my first supporting evidence. All right, and then the second one means when we have larger adjusted R-square, we also want smaller MSE, right? So the second evidence will be MSE. All right, so we want the MSE to be small as possible. So what is the MSE for Model 1? 2966, right? What is MSE for model 2, which is 371, right? Okay, so here we have the specific value. So for model 1, the MSE is 2966. For model 2, the MSE is 371. So which model is better? We say we want the adjusted R-squared as large as possible. We want the MSE as small as possible, right? So that means model 2 is preferred, right? So based on these two supporting evidence, which model is better? Model 2 is better, right? Okay, do we have another piece of evidence? Sure, right? So number 3, as what we test, we say what? We say for model 1, we can also look at the root mean square, which is SE, right? Okay, so that means we can also compare SE, right? So it's kind of the same supporting evidence, right? So for model 1, it is 54.46, right? So for model 2, it is 19.25. So we want smaller standard deviation of the residual, so this is preferred too, right? So actually I can list 3 reasons, right? So my question is, you can use these 2 as the 2 evidence. You can use the 1 and 3 adjusted R-squared combined with the SE as your supporting evidence. But can you use number 2 and number 3 as your 2 evidence? No, because they are the same thing, right? So you can either use 1 and 2, or you can use 1 and 3, but you cannot use 2 and 3 as 2 pieces of evidence because they are the same. Alright, so they are the same. Alright, so this is about E. Okay, so we kind of get the good idea about the first 2 models, right? So number 2 question, it says the model 3 is an attempt to model the number of weekly riders that use public transportation for the cities in the United States. All right, so A, how many independent variables are included in the model? All right, so let's look at model 3. All right, without the output, I don't know what's going on, right? Okay, so actually, this is model 3, right? So it kind of, we want to model the number of weekly riders using using how many explanatory variables? Where do you find the information? You can either find from here, or you can find from parameter estimates, right? Okay, so from here, remember it is K, right? The degree of freedom of the model is just how many explanatory variables included in this model, right? So you can either look at here, or you can count how many variables in the parameter estimates table. So how many? 3, right? Okay, so let's enter the first question, number 3. All right, so next, which of the variables in the model, some of you may think that how many independent variables are included in the model. Some of you think it is 4, but it is not included the response variable, because the response variable will never be independent with the explanatory variable. There's always a relationship between these these four, right? So here is asking about how many independent variables included in the model. That means the same thing to ask you how many explanatory variables included in the regression. All right, stay at home. All right, okay, don't go out. All right, so number B, which of the variables in model 3 are significant at alpha equals to 0.05? Okay, so number 3, we have 3 variables, right? So the question is asking which of the variables in the model 3 are significant. If it is significant, that means the p-value should be less than alpha, which is 0.05. Right? So that means, is this variable, is the price per week, this variable significant? Yes, right? It is less than 0.05. Is this variable, which is the monthly income of writers, is this variable significant with alpha equals to 0.05? No, because it is p-value is larger than alpha, right? Okay, what about the last one, the average parking rates per month? Is this variable significant? Yes, because it is less than 0.05, right? So the question is asking which of the variables in the model 3 are significant. Will be these 2 variables, right? So we say the price, right, the price per week is significant because what? Because the p-value is less than 0.001, right? The other one is called the average parking rates per month. It is a long variable name. Is significant because what? Because the p-value is equals to 0.0464, which is less than alpha. All right, done. Okay, next. Referring to models 3, suppose the width of the prediction interval for the particular city is fairly wide and not very accurate. What do you recommend the modelers do to try and improve the model? Be specific with the supporting rationale. Okay, so this question is an open question. You can think about anything, right? I do not limit the answers to just 1 or 2, as long as you can think of, right? So that means, okay, so let's understand this question. It says, suppose the width of the prediction interval for a particular city is fairly wide and not accurate. So what does that mean? If the prediction is not accurate, that means your model is not good. It's not good enough, right? So we say that if we think that this model is not good enough, what can you do to improve your model? So first, from this output, right? Since this is not significant, right? So what you can do, just remove this variable, right? So since it is not significant, that means with the price and the average parking rates in the model, adding monthly income of riders doesn't contribute to this model, to this regression, right? Okay, so this monthly income of riders is actually useless, right? Okay, so first option, what can you do to improve this model? You can remove the variable which is the monthly income of writers, right? And then see whether the MSE decreases or adjusted R-squared increases, right? Okay, so this is the first thing you can do. What else? They say if the regression is not accurate, is not good enough, there may be some transformations you can do, right? You can do natural log transformation, you can try the squared transformation, you can try the interaction transformation, right? So you can try everything to improve this regression. It doesn't matter, right? So number 3, since the variable of monthly income of writers doesn't contribute to this regression, maybe we can try to add some other variables into the regression, right? To see whether the adjusted R-squared increased and MSE will decreased, right? So all of these ways we want to see the adjusted R-squared increase, the MSE decrease. All right, so the last question. This question is separate with number 1 question, number 2 question. This question is just a separate question, right? So it says, write the population regression model. Write the model form you would suggest if the scatter plots show a quadratic relationship between y and x1, a linear relationship between y and x2, and a quadratic relationship between y and x3. Then what will be the population regression model you want to set first? It looks like a strange question, right? You don't have any clue for now, right? So now let's just figure out one step by one step. So first, it says the scatter plot shows a quadratic relationship between y and x1. Until here, what will be the regression model? What will be the population regression model? If the scatter plot shows a quadratic relationship between y and x1. First, the population regression model will be mu y. Well, we need a intercept, right? And then we first just focus on x1. We say there shows a quadratic relationship between y and x1. That means there is relationship between y and x1 squared, right? But remember in the chapter video, I said if you want to add a kind of transformation term into the regression, you need to add the original variable into the regression first, right? So that means you need a original term of x1, and then we have a quadratic relationship between the y and x1 squared. That means we need another term which is about x1 squared. All right, so that means until this step, this is our population regression model, right? And then we also see the scatter plot. From the scatter plot, we also see a linear relationship between y and x2. So a linear relationship between y and x2. Then we can keep adding it, right? So it would be what? We have beta 0, beta 1, beta 2. Then next one will be beta 3 with x2. because it's linear relationship, right? So we don't need to do any transformation. Now, this is already done with this step, right? Next, a quadratic relationship between y and x3. So this is the same thing for x1, the same situation for x1, right? So it shows a quadratic relationship between y and x3. So that means we have a x3 square term. But before you add the x3 square term, you need to add the x3 itself into the regression first, right? So that means we'll have beta 3. So next one will be beta 4, but with the x3 variable. And next one will be beta 5 with x3 square term. All right, so this is the model, the overall population regression model, right? So why I want to add this question into this assignment is actually I want you to learn about something. It's about why we always talk about population model and the sample regression equation. What's the difference between these two? All right, so the population model is actually you just set from the scatter plot, you have a general idea about the response variable and your explanatory variable. And then you can guess what is the population model then. All right, so once you set this model, then you can use a sample to generate the sample regression equation to estimate this population model. So actually, when you write this population model, you do not need any sample. You don't need any data. You just based on the actually you need the data. You need to have the scatter plot, right? So actually, you just based on the scatter plot, but you don't need to do anything about the regression, right? You don't need to know what is the detailed value of B0, B1, B3, B7, something like that, right? So based on the scatter plots, once you have the general idea, you can have the population model. And then based on the sample, based on the software, you can estimate this model, so that we call it is sample regression equation. All right, so we are done with this assignment. Hopefully you can get, oh my. So based on this assignment, I want to, hopefully you can get a better idea about the differences between the simple regression and multiple regression, right? And you get the general idea about the simple regression and multiple regression. So I kind of give you a review for the exam too, right? Okay, so good luck, guys.